Banach state house theorem. Very simple. If you want, you can start to prove it just now. Okay, I'll just give you the proof of this, and you feel that. Because giving the proof of that, I will remind you the theorem, the Baer theorem. You use it, Baer theorem. It's very important. Here we suppose that letter X, which is a complete metric space, this one, and also SI like this, a family of for also of closed subset or closed subspace of X, such that you have this condition: the union of X mark for X 0 to infinity must be equal to X. That means that SY covers this color covers of X in continuity. This one it must be the one. I can say that this one I belong to infinity. So your family is wonderful. Then you have this condition. Then there exists N0, which is this, said that the interior of this kind of 0 is not empty. Yeah, it's empty. That is the Baer theorem. So use this Baer theorem to prove our theorem is this the Banach house theorem. Okay, let us prove it easily, simply also. This Banach theorem. For the proof, the Banach house theorem, this one, the Banach house theorem. Let's say that first of all, Sn like this, the S, which is the X, said that the norm of I of X is that of I, and this one, and it's easy to see that. It's easy to see that the union of Sn from n1 to infinity is equal to X. You can prove it in very simple. You just prove that X is contained in the union this one, Sn. We just prove this. We just verify this one, which is also simple. Because if I take S here, if I take X in the element of F here, so I will try to prove that this one is contained in this kind of function. We know by the first property, the assumption that the supplement of T Rx is finite for all I in that form. So you use it to prove it easily. Okay, let me see. Let me prove it for you. We say that we say also, so you know that for all X in X, the supplement for all X to Ti of S, the normal is finite by assumption. Then there is this N0 in it. It's like that this one, Ti of X, the norm must be equal to N0. Then X is the element of N0. S, then S is contained in the union of S and 1 over T. Very, very simple. It's just that. You cannot, this is bounded, bounded by a real number. If you take the integer part of this real number plus 1, you can get an integer n0, which is the limit of n. You should show. And from here, you have this condition. Then you have the interior of this one is necessarily not equal to 0. That means that there is this x0, which is in the interior of this one. Is this one in interior and this 0? So that the ball of R in 0 is contained in N0 by the definition. Then we have this kind of function. The bar of this one is contained in N0 because this one is interior of this one. This is the resistible side that this one. The resistible, the resist R side that we have this condition. Here, that means that you have x0 plus R B1 0 is contained in S N0. That means that means that the element of this one, the element x equal to x0 like this, plus R Z is the element of S N0. This kind of. And I use the definition now of Sn and to prove to give the last result. Then when you have x0, which is x plus R z is n0, that means that the norm of this one is necessary of this one. That is the norm of ti of x0 plus R z is less than by definition of the norm. By definition of x n0, we define it for like this condition. And then you have ti x0 plus R ti z. The norm less than x0. Then the norm of ti z is less than x0 minus the norm of ti x0, this one, and to over R. If you take the supplement of this one, you have the norm of this one, the ti of this is less than 1 over R n0 plus the norm of ti x0. You have this condition. Then you have what you are going to prove. I just put, I then take the supplement of t, the norm of ti z, the norm of this one, and in the volume ball exactly the norm of ti. Then you have also that is the proof of the Banach Stenhouse theorem. Okay, thanks.